As you can probably imagine, the lower back takes a pounding on a day-to-day basis. If you lift something with an incorrect posture, if you slouch in your chair, or even if you're hunched over an operating table like a surgeon, all these things can lead to lower back ailments, which, considering its proximity to the spinal column, can be debilitatingly painful. Here at the University of Michigan, we are conducting research to aid in the creation of a solution to the problem of lower back pain. Hello, I am Ravesh Sukhnandan, a native of Belize, Belize, and when I'm not impersonating a doctor, I am a senior in mechanical and electrical engineering here at the University of Michigan, and I am a small part of the solution to the problem of lower back pain, as my short project for 2013 is the Therapeutic Back Brace under the tutelage of Professor Kira Barton. This project is an offshoot of the research Dr. Daniel Johnson did for his dissertation. From his research, he found that by applying a corrective moment from an actuated brace, you could reduce the force required by the back muscles to support the abdomen and thorax. Soon after, he co-started a company that hoped to commercialize this back brace, with the target consumers being individuals who suffered from lower back pain or who were in a fixed position for prolonged periods of time, like surgeons. The initial prototype for the back brace was limited in what it could do. It could apply the corrective moment and prevent damage to the lower back, but it could not distinguish between different motions. For instance, bending laterally and bending forward were interpreted to be the same motion by the back brace. And this meant that the back brace could not provide support for the user performing different actions in their day-to-day life. This led to a collaboration between Dr. Johnson and Professor Kira Barton, who has expertise in the areas of control and manufacturing, with the explicit aim of introducing human-in-the-loop features to the back brace. These human-in-the-loop features essentially mean that as the human user performs different movements, the back brace interprets these movements and takes an appropriate action to correct for these movements or provide support by using predefined control algorithms. Before these algorithms could be developed to detect and distinguish between different motions and subsequently correct and provide support for the human user, we needed to perform tests to collect data from actual human subjects performing these different movements and actions. This was my original task for the summer, where I would be supervising human subjects as they perform these different movements and actions in a controlled environment. While they were performing these different movements, they would be outfitted with an array of sensors that would be collecting data. After the tests were completed, I would analyze this data to see if there were any trends present in the data. Key among these sensors was an Arduino Uno based soft brace that takes measurements of force, gyroscope rate data around X, Y, and Z axes, accelerometer data in X, Y, and Z axes, and time data. The Arduino Uno based soft brace was designed and developed by myself and Dima Tota, a graduate student in mechanical engineering and my predecessor in this project. In total, the soft brace measures 19 datasets. Before I continue, I would like to ask you to look at the computer or device on which you are viewing this video right now. I can almost guarantee that it has some serial port on it. Indeed, the serial communications protocol has become the standard of choice for many computing peripherals, including keyboards, mice, and headsets. The Arduino Uno, the brain of our soft brace data collection unit, primarily communicates with the computer through a serial connection. The Arduino has revolutionized mechatronics, bringing a flexible and inexpensive platform on which to develop an array of mechatronic and electronic projects. However, the Arduino was not well suited for data collection because in its native state it could not handle high sampling rates, which in our case meant over 100 Hz. This is because the Arduino Uno's microprocessor is single core, meaning it can only execute one command at a time. Thus, when you have 19 datasets to transmit at each sampling instant, the serial communications protocol cannot keep up with this amount of data, and this stalls the Arduino from executing any other command. This causes our sampling rate to top out at 30 Hz, whereas other kinematic experiments involving humans usually have sampling rates well above 100 Hz. This slowed down our progress immensely, and thus my job description morphed from the person conducting experiments to an embedded systems designer. The solution to this problem involved utilizing a real-time operating system on the Arduino Uno and also transmitting the data from the Arduino to the computer as pure binary rather than as binary and ASCII characters. The Arduino, because it is open source, has many libraries and functions available to it. But the downside of this is because it is open source, the people who are developing for the Arduino are oftentimes doing this as a hobby, and so these functions and libraries may work, but they may be inefficient. What the real-time operating system does is to efficiently schedule tasks so that Arduino does not waste time performing one task or waiting on a task to finish while it could be doing another. This effectively mimics the ability of computers and microprocessors with multiple threads which are able to do multiple tasks simultaneously. This, coupled with the ability of the Arduino to transmit data as pure binary, cuts out the middleman of converting the binary data to ASCII human readable characters. And these two solutions were enabled us to achieve a sampling rate of around 250 Hz. Transmit pure binary as binary and utilizing a real-time operating system are common solutions in the embedded systems world. However, as I had limited exposure to microprocessor-based applications and programs, I was unable to come to this solution in a short period of time, and the majority of my summer was spent not performing the experiments as I was originally scheduled to, but implementing a real-time operating system based on William Grayman's code onto the Arduino-based soft brace, and subsequently developing a scheme to transmit data from the Arduino to the computer and developing software code to translate that binary code on the computer back to human readable ASCII characters for analysis purposes.
The final part of my research was the creation of a MATLAB program which should greatly aid the next person who conducts these tests in the analysis of the data that they get from this test and for spotting trends among the different movements. This program can plot data from both the Arduino and the EMG. We enter 1 because we want to have one axis, and we enter 2 under MPU because we want to have two Arduino lines on that axis. We select a forward test for the first Arduino, and we select a lateral test for the second Arduino. Next, we create the plot and we add two lines to it, and then we select forward first, and we select time against gyroscope X data against time, and then we select gyroscope X data against time for the second Arduino plot. We select the different options such as line style, line color, marker edge color for each one, so we can distinguish between the two of them, and then we plot the data. We notice that the gyroscope X data for both of them is very similar, and this would indicate that using that data alone we cannot control and we cannot adjust for the different movements because they are very similar. In concluding, I would like to thank Professor Kira Barton and the SHORE program for giving me this opportunity to conduct research at the University of Michigan, Dr. Daniel Johnson and Dima Tota for their patience and hard work over the last few months, Professor Emily Moore Provost for her advice and support, William Grayman and Jeff Roberg for the libraries used in the Arduino, and Electric Pig and MobileHealth.com for their pictures of the Kinect and Q sensor respectively.